Hello, I'm Tim Weaving, a PhD student at University College London, and I'm pleased to welcome you all to the 18th instalment in CompBioMed's e-seminar series in collaboration with the Virtual Physiological Human Institute, or VPHI. The talk today will be given by Michael Bareford, who conducts research at the Edinburgh Parallel Computing Centre, or EPCC. He joined the EPCC in August 2014, where his day-to-day activities involve helping researchers run their parallel codes on the Archer 2 and Cirrus machines. His remaining time is spent doing computational science research, such as investigating the benefits of using one-sided communications and exploring the suitability of FPGA devices for HPC workloads. Exaflow and NextGen IO are examples of projects he has contributed to at the EPCC, with the former concerning the need to prepare computational fluid dynamics codes for the move to exascale platforms. In today's talk, Michael will discuss containers in the context of high-performance computing. Containers are a convenient means of encapsulating complex software environments, but the question is whether this convenience can be realized for parallel research codes. Michael's presentation will explore a workflow that attempts to achieve this aim using Singularity containers that bind to the MPI libraries on the host. Now, before we begin, I'd like to briefly remind you that the session is being recorded and will be available on the CompBioMed website and YouTube channel shortly. So please do use this to go back over parts of today's talk and others in the series, and maybe even share these e-seminars with your friends and colleagues. There'll be a Q&A session at the end of the talk, so please save your questions until then. Then once the talk is finished, you can post your questions in the questions tab, and I will read them out to Michael to keep the session running smoothly. Now that's everything from me. I very much hope that you enjoyed today's talk, and without further ado, I'm going to hand over to you, Michael.
Okay, thanks Tim, thanks for the introduction. So my talk is entitled HPC Containers ? What I'm trying to do is explore the viability of running containers in a HPC context, running containers that contain parallelized codes. Now I believe the term containers was inspired by shipping containers. A shipping container has a standard shape, size, and construction, and it is this standardization that does so much to minimize the cost of transporting goods around the world, at least until recently. There's recently been an issue with container ships being too large. But anyway, back to the analogy. Just as a shipping container might hold one type of good, then any one HPC container should be dedicated to a specific parallel research code. Just as a shipping container can be handled by many ports, it should be possible for one HPC container to run on multiple HPC platforms without loss of performance, and that's the key point. The longer your code runs, obviously, the more money it costs. So these were, I thought, the aims that if you could achieve those, would make containers a good fit for HPC. But the effort required to do this is going to vary according to the HPC machine, the code, and also the run case. There is some uncertainty here. So I've started this work. I proceeded on a case-by-case basis. So I'll talk about, first of all, I'll introduce containers in a computing context. And then I'll talk about Singularity, which is a framework for containers that allows you to build containers and run them. And then I'll talk about how Singularity is integrated with MPI, because it's MPI, the message passing interface, that allows the tasks within a parallel code run to communicate. I'll show you some results early on. So these are results from a containerized GROMACS application running on Archer 2. Archer 2 is an AMD system. And then I will, having shown those, I'll talk about how I ran the container and then how the container was built. And I'll introduce the concept of the container factory. After that, I'll show some more results, but this time running on a tier 2 service that we host at EPCC called Cirrus. And I'll show you a containerized GROMACS, how it performs compared to running natively on the Cirrus CPU nodes and the GPU nodes. And then some conclusions. But first of all, what is a container? A container can be thought of as a lightweight virtualization, certainly compared to virtual machines. And it's important that it is lightweight, because you want to minimize the separation between the container and the host OS. Indeed, containers share the kernel of the host OS, and they can be thought of, another way of thinking of containers as a combination of Linux namespaces and control groups. So a namespace controls what processes can see, that is, those processes running inside the container. And C groups control what containerized processes can use. So this is important from a security perspective. When you run a container, the permissions that you have outside within your host account will basically stay the same. So what you can see and use on the host will be the same within the container. You will also have to have bound various paths, but that I'll come into later. What we wouldn't want to happen from a sysadmin perspective, definitely, is for your permissions to be expanded to be root level. But anyway, the container OS, because it shares the kernel, has to be compatible, which usually means that your container OS will also be Linux, maybe, for example, Ubuntu. So here's an image that shows the differences between a virtual machine and a container situation. With virtual machines, you have the hypervisor, which creates and runs virtual machines, and it presents the hardware layer to each guest OS. But with containers, we don't have that, because the container engine will actually use the host OS to access the hardware. And it's this understanding that leads, or in theory at least, we should not get a performance impact when we run containerized applications. We'll talk about the file systems now. The host file system is distinct from the file system within the container. As I said before, you are the same user inside and out, and it is straightforward to map a directory on the host to a directory within the container, which would allow you to maybe load any software modules, for example, from inside the container. Now, containers are typically immutable, so having a folder within your home directory on the host that is then mapped to the container provides a way to run a containerized application using different sets of input data. So this is actually rather useful, because input data can be large, and so this flexibility keeps container images manageable. Now, I say typically immutable as regards to containers, because you can generate writable sandboxes from a container image and then convert that sandbox directory back into a new image. And well, I'll talk about that in a few slides' time. So you can see in the diagram here, there's a folder on the host called home a user data that is then mapped to a folder within the container, which is just starting at the root within the container FS called data. Now, there is another container framework that you may have heard of called Docker, and there are differences between Docker and Singularity that really do make Singularity a better fit for HPC. So Singularity, the containers are well handled as files, or SIFs, Singularity image files, and then they are instantiated as a container when you run them with Singularity. Docker, on the other hand, uses overlays that are combined to make an image, and inside a Docker container, the user has escalated privileges, effectively making them root on the host system, which is what you definitely don't want in a HPC environment. So Singularity has the benefit that you run entirely within user space, so there's no administrative level privileges required to run containers on a platform where Singularity has been installed. Also, Singularity will support the high performance interconnects that are the means by which different processes or tasks that are running on separate compute nodes but are part of the same job can communicate. So essentially, Singularity is designed for parallel execution. There are two situations when you do require root permissions for using Singularity. That's namely when you come to install that software. This normally isn't an issue because installation of Singularity will be handled by the sysadmin, and they of course will have root access anyway. But it is indeed possible to install Singularity without root access. You have to specify a particular configure option, this without set UID, but that has the drawback of forcing all containers when they run to be run from within sandbox directories. That means that if you're running, say, on a fully populated node, so you've got maybe like 40 cores on the node, so you've got 40 separate sandbox directories needing to be created, that setup time will eat into your runtime, and not to say the available memory. So this is generally not a practical means for using parallel containerized codes. The other time you need root access is when you're actually building the container. And this is because when you first build it and you need to set up the OS within the container, and you'll need to download various packages from various Linux distributions. And when that software is installed, it assumes, or it requires that it's root that's doing the installation. So for this, because of this restriction, you would set up a container factory somewhere where you have root access, and then you can compile your code at the factory. But then you have the drawback of this in that when you're compiling your code on a platform that is separate to where the code will actually run, it's harder to make sure that that code will run in a performant manner. You also may have issues with compiler availability. If it's a GNU compiler, then that's fine. But if it's something like Intel or Cray, there may be license restrictions there. So I just talk about now how Singularity integrates with MPI. So ideally, we'd build the container such that it contains an MPI implementation that is identical to the one on the host. You can have something that is at least ABI compatible, applications binary interface, and there are several MPI implementations out there. There's Open MPI, there's various ones derived by from MPitch, and there's Intel MPI also. Apart from the first of these, Open MPI, the others have combined to form this ABI compatibility initiative. So that means that you could build a container that, say, has an MPitch MPI, and that should then run on a system, on a HPC machine that has an Intel MPI installed. There are two solutions actually for integrating the container and the host with respect to MPI, and I'll cover them both. So the first one is called the hybrid model. And what I'm showing you here is just the simple command that you would use to launch a containerized application, a parallel application. And what's happening under the hood, as it were, is that when you run MPI run, the parallel job launcher, then that starts up a process management daemon, which then calls the Singularity executable with the CIF file, which exists on the host. So that's colored in green here. And then at that point, the container takes over. The namespace environment is set up, and then the MPI application is called, which will then link to the MPI libraries that have been installed in the container. And then finally, when the code is actually runs and you're having to do things like various MPI collectives, or you're communicating data across all processes, then for that to happen, control has to go back to the process management interface on the management daemon on the host. And in this way, you can run a containerized application on multiple compute nodes So obviously, when you've built your container at the factory, the MPI there must be compatible with the host MPI, and it must be configured such that it is optimal for the host hardware if you're worried about performance. If you need it to be the case that the performance is more or less the same as it would be if you ran natively on that platform. So that step might be a bit tricky to do when you're building in a separate environment anyway. There is another model that Singularity provides. It's quite similar, or it's simpler actually, called the bind model. So this is when you don't have an MPI library inside the container. You just have your MPI application there, obviously. And then, well, the MPI run command is as it was before. But the MPI application, when it runs, it will link directly to the MPI library on the host. So you need to find a way to build that application such that that is the case. It's with the bind model, things will be easier to build typically. Well, there's less to build. Namely, not only do you not have to build an MPI library, but you wouldn't have to build any software that sits in between MPI and the containerized application. So this might be something like file IO, such as HDF5, which can it's a parallel file IO library, or things to do with linear algebra, such as the mass kernel library, and also fast Fourier transforms as well. So that means that takes out a lot of work when you're constructing the initial image, and also things are less painful if you want to change anything later on and you need to rebuild the container. There's not so much more software to rebuild, and you should be performant also if you're actually linking directly to the MPI libraries and such on the host. So my forthcoming examples where I've run containerized application, the GROMACS application, or used the bind model. So here are some results straight away. I'm showing you some strong scaling results. So it's core count along the bottom, and it's runtime in seconds on the y-axis. And this is GROMACS 2021.1. This is for a particular benchmark involving 1.4 million atoms, and the code both that ran natively, or the so-called bare metal run, and the containerized app used the Cray MPitch library on the Archer 2 4-cabinet system. So on the right, I just give the hardware spec of Archer 2. So it has 128 cores per node and so on. So it seems like in runtime, the two sets of results, those that are done using Singularity version 3.5.3 and those that were run just straightforwardly on the compute node, are the same, more or less, are comparable. I show a different value on the y-axis now. This is the internal performance metric produced by the GROMACS code, and this is nanoseconds of simulation time per day of runtime. And what I actually did for each core count, for each plot point, I ran the bare metal version 3 times, and then also ran the Singularity version 3 times. And then the plot point is the average of the 3, and then the horizontal bars are the maximum and minimum performance. So we see there's quite a lot of overlap in the results, which leads you to believe there isn't much difference between bare metal and Singularity, and indeed on a few occasions the Singularity does lead, but that's just artificial. I mean, I think if I was to run things enough times, I would get greater convergence still between the two sets of results. I also ran a larger benchmark just so that I could run on more Archer 2 nodes. That brought me up to just over 8,000 cores. So it's a 4 million atom protein in water benchmark. And I took an average of 3 runs, and I found that the containerized performance was slightly better by about 2% or so, which is surprising given that I'm using the same Cray MPICH libraries and the same fast Fourier transform library too, same compiler. So I think what was a fact here was node assignment. So the nodes weren't quite the same that were used for the containerized run as compared to the bare metal. And so there are differences in compute node performance that were outweighing the overhead due to containerization. But that was a promising set of results. So now I just talk about how I actually ran the containerized GROMACS and what I actually did. So what I'm showing here is the outline of the Slurm submission script on Archer 2. So Archer 2 has a Slurm batch system, and the heart of it is obviously where the parallel job is launched, and you can see srun, the parallel job launcher, and that's pretty much the same as it would be if you're running on bare metal. You just have this singularity clause in the middle there. So I'm doing various things. I'm passing options to srun, which control the way the MPI tasks are pinned to the CPU cores. I then also specify the directory from which the job is run, this @run path. And then when I call Singularity, I'm executing the Singularity image file as indicated by the sif argument. And then I'm also passing something called bind_r, which specifies the linkage between the host file system and the container file system. So I also need to specify an environment script, which will set up an LD library path that the containerized application will use, and then that allows GROMACS in this case to find the Cray MPICH library, which lives on the host. You'll notice I'm using some color coding here, green to indicate paths on the host, and orange to indicate the container. Obviously, the application executable is inside the container, but the app_params is not. But this is possible because my bind arguments have shared the folder that contains the input data. So that allows the containerized application to access that input data. There are a few steps before I run srun that need to be done when you're in a containerized, when you're trying to run a containerized application. And so I talked about the bind paths. I need to set those up, and actually I need to run the Singularity image such that it will run a particular command that will output the bind paths that are stored within the container, but they're stored against a particular HPC platform, in this case Archer 2, and this is the bindpaths.list file. And then when I've got that and I've basically assigned it to an environment variable inside the script, bind_args, I then append to that to allow some paths that are kind of dynamic and that I'll only know at runtime. So this is obviously the path to the input data. So I just show you in this insert here what's actually in the bindpaths.list file, and so you've got various paths such as this opt Cray path, which allows the containerized application to find the Cray MPICH libraries, and also you've got various other paths too. When I bind userlib64, I need to have a different name within the container. So that's the reason for the colon there, because obviously the container has its own USR lib64 folder. Now onto the environment that the container needs, well, I should say the LD library path environment variable. I do the same thing in that I execute the Singularity image file such that I output the content of an environment script that's held against a particular combination of HPC platform, MPI library, and compiler. So that's the CMPICH8 and GCC10. And I output that into an environment script that's held on the host, because I'm now going to pass that environment script to the M file option in the Singularity command below. So there is a caveat here in that older versions of Singularity, such as the one running on Archer 2 4cab, they don't support this M file option. So what I needed to do was go into the environment script once it was on the host and just use a sed command such that I would I would prepend export Singularity env to the LD library path definition. And that means that when I run Singularity, that environment variable is then picked up, and then the setting becomes the LD library path inside the container. So you may be wondering what actually is in the environment script. Well, here are the gory details. You can see I've got my path to my MPI library that starts opt cray, and then the LD library path at the bottom of the script is set up. So I've got the paths to the FFTW library and the libsci, which is the linear algebra library, MPI root. And then I've also got paths to some InfiniBand verbs, which is like an interface, a low-level communications interface. So the IB is a bit misleading here because, of course, Archer 2 uses the name temporarily escapes me. It uses a different interconnect, slingshot. But at the end, you've got the number of paths that are required for the containerized application to run. So now, I mean, it's fairly straightforward to run a containerized application. It's not much different to when you run on bare metal. But then how did I create the image file initially? So I've mentioned in passing something called a container factory. So this is a machine distinct from the HPC platform for which I have root access. And in this case, I use something that the University of Edinburgh provide, a research cloud service called Eleanor, which is based on OpenStack. And I can run that up, and then I can, the Eleanor service allows me to control that instance, so I can stop and start it as I wish. Now, I could have set up a container factory on my personal laptop. I have root access there, but it was important to do something so it was on a separate instance, on an instance that was dedicated to the container factory, just to avoid being dependent on any details that are peculiar to my machine. And also then it requires that I need to set up scripts, not only to build the factory or create it, but then to also create container images from inside the factory. And so that can be documented in a GitHub repo. And so everything is nice and reproducible for anyone else who wants to create their own container factory, such that they can containerize their own applications that they are using. So Eleanor is quite nice, though. It provides an interface that you access through a browser called Horizon. So there's just a few more details of the resources that my factory instance used, 8 CPUs, 16 gig of RAM, and so on. It runs Ubuntu 20.04, and I have the latest version of Singularity. I think 3.8.3. I think that's still the case. But anyway, once you're in the factory, and then you go to a particular builds folder. So I'm using a purple to indicate paths within the factory file system. You can then build your initial image. So you actually just use a simple Singularity build command, for which you do need root access, hence the sudo prefix. And the main input to that is something called the Singularity definition file, this .dev file that you see there. And when the build command completes, you'll have created your image file called GROMACS.sif.0. So what's in a definition file? So the most important thing actually at the top, where you specify what sort of operating system will be used for the container, and in this case it's Ubuntu 20.04, and then the rest of the definition file is split up into sections, and two that are most important here are one called files, and this is where you take various files or scripts in my case, or a script archive that live on the factory, that they actually were cloned from the repo to the link that I had up on an earlier slide. And then these are transferred to the opt folder within the container so that they're available to the container. And then in the post section is basically where you build the container, when you add the extra things you need once the operating system has been set up. So the first thing I do is actually run something called Ubuntu. Well, after doing the post_start, which unpacks the scripts archive, I then call a Ubuntu 20.04 script, which installs some other packages that I need. And then I install a Minicon environment, and then I install CMake, which will be required to build GROMACS, which will be done on a HPC platform. And then I download the GROMACS source. So the definition file, you can have, there are many other sections. And if you want to find out about those, you can consult the Scilab's Singularity user guide. I've got the link there. So I'm just showing you what's in some of these scripts. So in the Ubuntu scripts, I'm basically, so I'm setting up various sources, and then I install some other packages that I'll need. I have something called Squash FS, which is provides a compressed read-only file system for Linux-based containers. I also have things wget and git, which I'll need to download various things. And then I'll have a bit where I install the GCC compilers, and the argument that I provide to this script, the 10, just specifies the version of GCC or G-Fortran that I want. And then the source script for the GROMACS code is quite straightforward. I'm just doing a wget from the FTP GROMACS site, and then I've got the source code. Once I've done that, it's important to understand the provenance of the container, and you can use something called you can use the Singularity inspect command with the -h option, and then that will produce the text that you see in the box, and then it tells you exactly how the container was created, and it will give you the path. So the path that's pertinent to the container file system that shows you the output that happened, that was created during the creation stage. So that's basically, you know, what packages were actually installed as part of the Linux OS, and what was the output for when the CMake meta compiler was built. And also it gives you the path that's inside the container for the original definition file. So it's always possible to access any file inside the container. You can just use this example of a Singularity exec command that I give below. You just use the cat command. So the idea is this provenance history will grow every time the containerized application now is built on or targeted at a HPC platform. So it's important that just having the image file, you can specify, if you run the inspect command on it, you can then know where that container was built, when the initial image file was built, and also which platforms it's been targeted at, and which MPI libraries were used, and which compilers were used, and so on. So I'll just talk about the next step now. So I'm at the factory and I want to target my container. So I have a top-level target.sh script. So I specify my application, which is GROMACS, my HPC platform, which is Archer 2. I then specify the path on Archer 2, which is within my personal user account. I mean, this is just an example here. So that's the path within which the GROMACS will be built inside the container. And then I've got some various other details which indicate the GROMACS version, as well as the MPI library and the compiler. So that's a top level, that's just the way that the target script is called. There are, so just not too long ago, actually, with the release of Singularity 3.7, there is a further requirement now that bind paths, so it's for bind paths that already exist within the container. Sorry, I'll start again. So this new, the newer versions of Singularity, in order to improve their security, they now require that bind paths that already exist within the container must already exist within the container before those same paths can be used with the -B option. That's when you need to execute the container. So I try to explain that with an example. So on Cirrus, for example, I would normally just bind these paths that exist on the Cirrus platform. So that's the Lustre SW and the Opt HPE. So previously I could do that without those paths having to be created inside the container. But now that's with the later versions of Singularity, I now need to create those paths within the container before I begin the targeting process. So in short, I need an extra script that just comes before I call the target.sh, this target init. And so the targeting script itself is just split up into 3 sections. The first one, I just upload from the factory the initial container image to the host. I do that. I run something called a deployment script, more on that on the next slide. And then once in the deployment phase is when the containerized application is built. So now I've got a new image, which I'll now download back to the factory. So what happens at the deployment stage? Well, the deployment involves locating a script that exists on the factory, and then I specify the various arguments that I'm going to pass to that deploy script, and then you can see just here, if I'm moving my mouse pointer, I'm running the SSH command in order to run the deployment script within a bash context on Archer 2. And that's what I do. So what happens inside the deployment script? Again, that's also split up into 3 sections, where so now I'm on the host, and then I convert the Singularity image that I uploaded previously. I convert that into a sandbox, and then I build my application within that sandbox. And then once that's done, I can then convert that sandbox back to an image to be downloaded back to the factory. So again, the middle part is the interesting part. What happens there is I execute the Singularity image file sandbox now, but as a writable sandbox. And what I'm doing, if I can just use my pointer option. So what I'm doing is I'm specifying the path that exists within the container. I'm using the orange color coding here, which basically controls how GROMACS is built within this sandbox. And as it's built, it will use this particular MPI library. The Cray MPitch 8-OFI. So I mean, I've thrown up a lot of scripts, and I've gone into a bit of detail, but this graphic here just summarizes the whole process. So I'm in my factory in purple, and I run a target script, which then it does various things. That will upload the initial image file to the host, at which point then a deployment script is run on the host. And then as part of that then runs a build script within the container sandbox. And so if I go back to the provenance information that I talked about before, and so what you're seeing now is the same information that you saw when I first created the script, but down below you've got 3 extra lines that show the output from 3 successful targetings. The first 2 were both to Archer 2 for Cray MPitch and for the Open MPI library on Archer 2. And then also the third one is for Cirrus using the HPE MPT library. And so each of these, the builds produce a log file, which is within the container, and then you can then consult that but by just running a Singularity exec cat command. So as I've targeted at Cirrus, I'll show you some results from there also. But first, with it being a different HPC platform, unsurprisingly, there were things that I had to do that weren't quite as, well, there were extra things I needed to do compared to targeting for Archer 2. And namely, I needed to copy across some Mellanox libraries, some libraries to do with the InfiniBand interconnect on Cirrus. And to do that, I needed to create a specific folder within the container sandbox, and then just copy over the libraries that I needed across. Now these libraries exist in a /lib64 folder on the Cirrus host, and unfortunately trying to bind directly to lib64 caused problems because there were incompatibilities between the libraries within Cirrus lib64 and those libraries within the lib64 on the container. So this is the extra step I needed to do. And also when I actually build the application within the container sandbox, I needed to specify an extra option for the command that executes the build script. So this is this no home option, and what that does is it prevents the user's home folder on the host from being mounted inside the container. And I needed to do that because on Cirrus, the home folders exist within this Lustre SW path. Sorry, that's true. They exist within the Lustre folder. And because I was binding to other things within the Lustre folder, such as this SW folder, then that caused a conflict there. So I needed just to restrict or prevent the binding of the home folder. And then I found that I could build the application within the sandbox. So once that was done, that was converted back to an image file. And here are the results for, again, it's the same benchmark, the same GROMACS benchmark, the same version, but running on Cirrus, and obviously using a different MPI library, HPE MPT version 2.22. And on the right, I'll just give the spec of the Cirrus machine. It's a tier 2 machine, so it's not quite as good as a spec, or not, certainly in terms of number of cores per node. So you can see the two sets of results are quite indistinguishable. Sometimes Singularity leads, sometimes it doesn't, but they're all fairly close together. If I was to run, instead of doing 3 runs per plot point, I think these results start to converge. I did the same, so this is running on the Cirrus CPU nodes. I did the same, but on the GPU nodes. So this is using NVIDIA Teslas. And things are are even closer in this environment. So now I'm using a different MPI. I'm using one available on Cirrus that was built such that it's CUDA aware. So I'm using CUDA 11.2. You've got the details of the GPU nodes on the right. So I scaled out to 60 GPUs. So I should say that each run is running on a fully populated CPU node, or it's always a fully populated node. And for a GPU node, I have 40 CPUs and 4 GPUs. And when I'm running on 64 GPUs, that means I'm using 16 GPU nodes. And as far as actually when I run the application, I use this srun, and then I need to pass an extra option to the Singularity, which is this -mv, which allows the container to find the various CUDA libraries and so on. There's an equivalent option if you are using an AMD GPU. I think that's just -rock something or other. But anyway, those results were quite good. So in conclusion then, well, at this stage, there wasn't a significant difference between the containerized and bare metal performance, and I think this is down to the fact that I followed the bind model as opposed to the hybrid model for my containers. So previously, I've used a hybrid model, particularly with regard to CP2K. I found that's another modeling code that I found that there was a performance impact there. But using the bind model, I've also seen similar results using the CASTEP code and also a code called Ramses on the Archer 2.4 cab. I think there are other things that I would like to try, such as I like to explore the use of other compilers. So everything I've done so far is just building a compiler that's installed inside the container. What would I do if a compiler required a license, such as an Intel compiler or a Cray compiler? Would it be possible to actually use the compiler on the host? It might be. I think it would be better to have the compiler in the container. You just have to see if you can get around any license issues. It might be the Intel compiler might be free to use if all you're doing is compiling software. You're not needing to profile it or anything like that. Also, everything I've done so far is using a particular processor architecture, AMD 64, the x86-64 architecture. What about if I want to use, if I want to target an ARM machine? Unfortunately, I can't use the same image file. I need to use a different one. But Singularity CE does provide a remote build facility. So I could be running on my factory, and then I could have a definition file, and I could specify this command with the remote option and then indicating the architecture. And that will take the definition file and build the initial image compatible with the ARM architecture. And then I could take that, and then within my workflow, I could just target that at various ARM HPC platforms. But of course, now for the same application, I would have to have two image files, one for AMD 64 architectures and the other for ARM. Another thing I've been wondering about, which might be an improvement, is to use something, this is a Singularity concept called persistent overlays. I wonder if it's possible. What a persistent overlay is, it basically contains the deltas or the changes that you've made to a base image. So it might be possible to have an overlay that encapsulates the targeting work that you've done, that it encapsulates what's required to target a base image to a particular HPC platform. And then so you could then have multiple lenses, if you like, or multiple overlays for the same image, and then they'll each apply to a different HPC platform. I don't know how easy that is to do, or if it's possible, but that would make an interesting masters. It'd be interesting work for a project. So everything I've talked about, all the scripts that I've shown, there are in this this GitHub repo. I've got the link at the bottom of the slide. But thanks for listening. That's the end of the talk. So I'll hand over to Tim for questions.
Fantastic. Thank you very much, Michael. Just a quick reminder for the audience, if you do have any questions, then please go ahead and write them in the questions tab so that I can read them out for you. So now whilst we are waiting for the questions to start coming in, whilst people are gathering their thoughts, I've got a couple of questions of my own for you, Michael.
Yeah.
So you've shown us the promising scaling for the Singularity containers on Archer 2 and Cirrus, right? But yeah, you kind of hinted that there could be a divergence from bare metal performance as the limits of computational resource are pushed.
Yeah.
And as we approach the exascale era, where might the bottlenecks lie for the continued scaling of these container techniques?
I think they will lie in memory, because when I'm running a containerized application, there is a slight overhead in memory per MPI rank or MPI task. So it's of the order of megabytes normally, or tens of megabytes, but that's per task. And so if you scale that up to the number of tasks that are on a node, it will be a few gigabytes. So when you're running if you have a run case where memory is tight, if you're trying to work with a particularly large mesh, then having that slight overhead in terms of memory from containerization may start to have an impact. So if you're trying to explore a new scenario for your research, which really puts the machine at its, which really stretches the machine, then that slight overhead that comes with using containers might be an impact there, might be a factor.
Right, I see, thank you. So the workflow that you presented here, could it be adapted for encrypted containers?
Yes, I think so. I mean, it breaks things a little bit. So when the container image is created at the factory, everything would still be in the clear, so to speak. But I guess that container will be, the access to that container factory will be tied down. And then when you've got the initial image, it can be uploaded to the HPC host. You'd use a secure copy command such as SCP. So I should just explain what encrypted containers are actually. So when you build an image initially, you would then provide the key or the public key that's going to be used to encrypt it. And then once you've got an encrypted container, all you can do now is run that container. You can't extend it further. So when you run the container using the exec or the shell or the run command, you then provide the private key such that container is then decrypted, but it's only decrypted within the kernel space. So anyway, to get back to my workflow, initially things will just be as they were, in that the upload of the initial image is done using SCP, so secure copy, to the HPC platform, and on that HPC platform you'd have a specific key pair, and then you go through the deployment phase, and then you build it, and once you've got your sandbox, and then you go back to an image from the sandbox within which you've just built the application. At that point, you then encrypt it under a public key. So, and then you've now got an encrypted image with hopefully a performant containerized application, and then you can distribute that image to those users that have the private key that would allow them to run the containerized application. So it breaks things a little bit in that I don't think you'd be able to have one container that can now run on multiple applications, because I think it would be better to set up separate key pairs for each HPC platform that you need to run on, just to avoid having to share a private key.
I see, I'm with you, thank you.
Yeah.
Okay, we've got one question that's come in here from the audience. Oh, sorry, that's another question about whether or not there'll be a recording. Yes, the session has been recorded, so yes, it will be available on the YouTube channel. I'm not seeing any other questions yet, so I'll continue with asking a few more of my own. Yeah. So I'm not entirely sure that I fully understood the functionality of the container factory. Yeah. So does this just construct container instances, or does it also perform some sort of additional workload and resource management as well, such as overseeing multiple containers life cycles simultaneously?
I suppose it could do. I mean, as it exists, yeah, it just creates container images for specific platforms. But I mean, how I see this might be of use is I imagine that, say, a research software engineer who's in charge of maintaining a particular research code would maybe have a container factory of their own, and then they would then target that at the various HPC platforms that they need to run on. So I think really it's kind of specific in to be able to just create container instances. But if you wanted to also build containers for other applications, you could do that. And then you could record their life cycle, which is indeed done, because I have the provenance information which you can access using the inspect command.
Right, I see. And so this kind of leads me on to ask about Google's Kubernetes, which is a system for orchestrating containerized applications. as I understand it, but I believe it's intended more for microservices. Although I read an article quite recently on the potential for HPC workloads to be managed by Kubernetes, or at least some derivative of, right? So is this something that you've given much thought to yourself?
No, not as yet, because I mean, I wanted to have maximum flexibility, so I just wrote everything in batch, but everything. So I wrote everything in using bash scripts, just so that if there was any fiddly detail that applied to a particular HPC platform, I could get around that. So I was shied away from using something like Kubernetes or Ansible, because then there would be an additional overhead there for me. If there was something particular about HPC platform which meant I had to make a change in a specific way, it's easy to do that if I've just got everything in bash scripts. And I just, it's just easier, just faster to be able to see whether or not you could run a performant codes. But I think maybe that there may actually be a reason for actually trying to transfer this kind of all of this to transfer all of those that work so that it could work within an Ansible environment. Or
Sure, I'm with you. So I'm not seeing any further questions coming in, so I'm thinking that maybe this would be a good point to draw the session to a close. So thank you once again, Michael, for giving us your time today to speak about containers for HPC. Just one final reminder that this e-seminar will be available on the CompBioMed YouTube channel and website, which if you just go on to the next slide for me, please, Michael, will be accessible via the link shown on the screen. And yes, finally, thank you to everyone in the audience for attending, and I hope that you all enjoy the rest of your day.